Today we're going to cover dynamic balancing of machinery, and what I'm going to show you is a couple of different scenarios using SOLIDWORKS Motion. Today what we'll cover is the differences in simulation packages. We'll cover motion basics, the interface with motion. We'll look at two different challenges, a simple system and also a motion of a piston and the forces acting on it. And I'll show you a video of a very complex system that was done in SOLIDWORKS Motion. And then we'll finish off with a summary of what we did today as well as some questions. So let's go ahead and get started. First, if you are a SOLIDWORKS Premium user, you are already aware that you have access to linear static FEA for parts and assemblies. You also have access to the Motion product that is built in. And if you're using Simulation Professional, you also get the thermal, frequency, buckling, fatigue, etc. tools, as well as optimization. We will cover optimization with Motion today. And also with the Simulation Professional, as well as the Simulation Premium package, you have event-based motion and also the ability to use motion-based optimization. And what that is we can do a design study and optimize our motion mechanism using design studies in SOLIDWORKS Motion. Okay, so the basics of motion. What we're doing is we're studying movement of mechanisms. How do our mechanisms react based on the loads, forces, accelerations acting on them? And what we're most interested with is finding out the loads and possibly taking that and doing finite element analysis on it. Now, the motion of our system is defined by or determined by four different factors. We're already familiar with mates and how those affect our component locations in assemblies. Another thing that determines the motion of a system is the mass properties of components. So if you're currently designing parts in SOLIDWORKS, one of the really nice things to do is go ahead and assign a material to that component, especially if you're going to then turn around and use those components or that assembly in a motion analysis. Another thing that determines the motion of our system are the forces that are applied to that system. That's the dynamic portion of how our mechanisms behave. And of course, lastly, the amount of time helps determine the motion of our system. And just a quick review, normally we're used to seeing sum of forces and moments equals 0. That's for a static system. However, with a mechanism that we're interested in motion, really what we're looking at is the sum of the forces acting on the system is equal to the mass times acceleration, and then the sum of the moments that are acting on the system is equal to the change in angular momentum with respect to time. That's what the motion product is actually solving for us once we set up our analysis. All right. As far as motion goes, there are really two basic kinds of systems. There's a kinematic system and a dynamic system. A kinematic system is such that there is only one unique solution for the motion. For example, a scissor lift, the only thing that really changes is we add more weight, we require more force to raise or lower the lift. The motion of our system is unchanged. Whereas a dynamic system, the mass and string example that I'm sure we've seen at one time or another, the motion of that system is really dependent on the mass of each of the weights and the length of each of the strings. In that particular instance, multiple solutions are possible based on simple changes to that system. All right. Now, as far as our motion interface, for those of you familiar with it, it is fully integrated into the SOLIDWORKS graphics window and environment, and it uses something called the Motion Manager. So at this point, what I'm going to do is switch over to SOLIDWORKS, and I'll show you exactly what that is. All right. So the first thing that I would point out is if you don't see this bar down here with these motion study tabs where I have motion study 1, hinge mates, and no redundancies, I can turn that on from my view menu, and I'm going to show the Motion Manager. So when this is checked, you will see these tabs. This is how we access a motion study. So when I click on one of these tabs, this is very similar to working with Excel. I have a couple of options here. If you're using SOLIDWORKS Standard or SOLIDWORKS Professional, you would have access to animation and basic motion. As soon as we're using SOLIDWORKS Premium or either of the simulation professional or premium packages, we have an option for turning on motion analysis. This is what allows us to create or to analyze our assemblies and get out the kinematic results acting on our joints. As you can see here, it's basically a timeline interface. This is the SOLIDWORKS Premium interface, not event-based motion just yet. But as you can see, we have different options for calculating our studies, applying motors or springs, dampers, forces to our system, or even applying gravity. The option here, calculating results and plots, I'll go over that as we set up our first analysis here. And then, of course, as we're all familiar with SOLIDWORKS options, we also have study properties for our motion analysis as well. All right, so the first thing that we're going to look at, a challenge of a simple system. You can consider this something very similar to a washing machine. For instance, a washing machine, as it spins, when it's full of water, the imbalance doesn't really matter, but as soon as the water is gone and the rotational velocity increases, you really have to worry about a net imbalance of forces acting in the system. Now, most washing machines, they have a lot of dampers and other systems built in so that they can take that imbalance as the spin cycle ramps up. So what we'll do is let's take a look at a very similar example in SOLIDWORKS Motion and how to set up a problem that would mimic essentially this imbalance that we would see due to the rotational velocity and the net imbalance of forces acting on a system. All right, so the first thing that I'm going to do is I'm going to insert a new motion study. And here the first thing that I'm going to do is take a look at the mates that came through direct from SOLIDWORKS. Now, for instance, you'll notice I have a hinge mate between one end of the hinge body here and then my crank mechanism, and I also have a hinge defined at the other end. Now, at this point, all I have to do is assign a motor, and just like SOLIDWORKS, we have our feature manager window that becomes active, and I am prompted for what the motion interface is looking for. So what I'm going to do is define a motor location here. It's as simple as clicking on a face. I have different options for applying that motor. In this case, we're just going to use a constant speed motor, and we'll set it to about 60 RPM and accept that. All right, from there, the next thing I need to do is just define how long I want my motion analysis to run. In this case, we'll just allow our motion analysis to run for a single second. And at that point, I also need to make sure I'm using the motion analysis tab and not just basic animation. And now I'm just going to click this to run my study. All right, so not much to the setup. What we can do from here is take a look at some of the results. For instance, I want to plot the reaction forces that happen on either of the hinges. So we'll look at a magnitude of, in this case, hinge 1. Now you'll notice this pop-up menu here. This has to do with redundancies. Now you'll notice down here with my mates, I have 5 redundancies due to my hinges. Now I'll explain that a little bit further. For now, what I'm going to do is tell SOLIDWORKS Motion no. All right. Now in this case, probably the magnitude isn't exactly what I was looking for. It's a 4 Newton force. So what I'll do is come back to my result plot. Just like anything in SOLIDWORKS, if I want to modify something, I can right-click on it and edit the feature. And then in this case, I will change to, say, the Y component of the resultant. And what we can see here is as our mechanism is rotating, we have a slight imbalance of the forces in the Y direction of our assembly. Now I'll do the same thing. I'll also plot the results for the second hinge. So we'll take a look at the reaction force, Y component of the second hinge. And I'll click OK. And again, no. And we have a second plot. Okay, so you can see here that regardless of which hinge, either hinge 1 or hinge 2, the direction of the force due to the net imbalance as this mass is spinning around oscillates very much like a sine wave. All right, now as far as the redundancies, let's go back to our slideshow here. When I take a look at redundancies, each solid body or each rigid body in an assembly has degrees of freedom. We have 3 translations and 3 rotations for every body. And as we're applying mates in SolidWorks, we really don't think about the degrees of freedom that we are removing from our assembly. For instance, it's very common practice to take a body and use 3 coincident mates on that component in an assembly. Well, each time you add a coincident mate, you're removing 3 degrees of freedom. So in essence, 3 coincident mates remove 9 degrees of freedom from our system when that component only has 6. That's where the redundancies come in. So you can see here concentric mates, they actually remove 2 translations and 2 rotations. The hinge mates that I used with that simple example actually remove 5 degrees of freedom per mate, allowing just the rotation about the z-axis. The last 2 that I'm mentioning there, coincident point-to-point and coincident point-to-axis, those are very important mates for using and setting up a motion assembly. And I'll show you exactly what I mean as we go back to this example here. So what I want to do is reuse this assembly, but I want to remove the number of redundancies that I have in my system. So what I'm going to do is I'm going to start a new motion study, and I'm going to actually switch to an exploded view that I have pre-created. And what I'm going to do within motion is I'm going to suppress these 2 mates that I generated within my SolidWorks assembly. Now the first mate that I'm going to use is a spherical joint between the point at the end of one of my hinges and the point at the end of my connecting rod there, or the imbalanced shaft. And I'm going to add a coincident mate to it, or a spherical joint. And you'll notice that that adds a local coincident mate in my motion manager tree here. Now that local mate tells me this mate is only active in the motion analysis. Now the second mate that I'm going to add is one between the axis of this shaft and a point on my opposite hinge. I'll add those, and I'm going to collapse my assembly. And then I'm going to do the same thing. I'm going to add a rotary motor, 60 RPM rotary motor, to the crankshaft. So other than changing the mating scheme, I haven't really made any additional modifications to that. Now when I run this motion analysis, well, tell you what, let's set that for just a single second, and I'll rerun it. Now I can take a look at the same plots, reaction forces on either of those mates, and you'll see that the results really don't change that much. Now that just happens to be because this is a simple example. If we had a much more complex model, you would really want to do everything you can to remove as many redundancies as possible. Make sure we're just restricting the degrees of freedom from our assembly, as few degrees of freedom in our assembly as possible, and make sure that we still allow motion in our system. All right, let's take a look at some design changes here from our unbalanced weight. One of the things that I can do, if I go back to my assembly, I'm going to change configurations of the crank. So here in this configuration, I have a balanced system as far as the mass goes, but each of these masses are slightly offset. So now if I go back to my motion study, I can rerun the analysis, and I'll see that due to now that the weights are balanced, that the magnitude of the reaction force is considerably less. Let me go ahead and plot the reaction force at the second mate that I added in this particular motion assembly. Take a look at the second mate there, and you'll see that those also are in line or in sequence. Let's take a look at another example here. let's say I have balanced weights, but they're offset a little bit. So if I look down the axis of the shaft, everything looks okay, but I see that along the length of the shaft, those weights are slightly offset. In this case, when I run this motion analysis, I get a much different result. The forces acting on one hinge are exactly opposite the forces acting on the hinge at the opposite end of this assembly. All right, let's take a look at one final example here as far as balancing goes. One thing to remember, when you're working in a motion assembly, I cannot change the configuration from directly within motion. I have to switch back to my model tab and change it within the context of the assembly. So let's take a look at 3 weights that are balanced and in plane. Now when I go back to this motion study and run it, I see that I have a perfectly balanced system. There is no reaction force at each of the hinges. All right, so that's a simple example. Let's take a look at our next example. This is a model of a simple piston. With a piston, one of the challenges is accounting for the magnitude and direction of the load as the connecting rod and the piston changes position with each rotation of our crankshaft. So as you can see in the picture here, this is what we have to account for. Similar mechanisms like jigsaws or orbital sanders or even windshield wipers have similar mechanisms. So one of the things that we really want to do is minimize the forces that are acting on the bearings in our system. When we get through setting up this particular model, the next step that we'll do is actually get into capabilities that are part of Simulation Professional and Simulation Premium, and that's actually optimizing the design of the crankshaft. So let's go ahead back to SolidWorks and take a look at our piston model. So here, as I rotate the crankshaft, well, all of my mates aren't following through. Give me just a second and correct that. We'll suppress these and unsuppress each of these. And now the motion of my system is exactly like I would want. All right. So just as before, what I'm going to do is create a new motion study. I could choose to reuse all of the mates from my SolidWorks model. I'll leave these there for now as I set up this motion analysis. So what I'm going to do is, with motion, I can add gravity. For instance, I can choose to have gravity acting along the axis, the vertical axis of this piston assembly. Another thing that we might have would be a constant force that's acting on the face of this piston, say a 20 Newton force always pushing down. So these are some options that we have as far as setting up our assembly. All right, if I do nothing else here, let's say I need to add a rotary motor. And in this case, what I'll do is apply a rotary motor on the crankshaft, and how about we make it 600 RPMs. All right, when I do that, obviously I don't need my motion analysis to run for 5 seconds. Probably only need a very short time frame. And in this case, if I do 1/10 of a second, I will get 1 full revolution of my motor, or the piston here. So let me go ahead and run that. And you'll see that once again I have a number of redundancies as the piston is spinning around. All right, I'm going to make one other change here. This happens to be in the motion study properties. Since I'm dealing with such a short time span, I need to increase the number of frames that my analysis is running. So what I'm going to do is set the motion analysis to 1,000 frames per second. That's going to give me 100 frames of analysis for this 1/10 of a second model here. All right. I'm also going to change the playback speed, and I'll rerun the analysis. All right, so at this point, since I'm really interested in some bearing forces, or the forces acting on each of these bearings here, what I'm going to do is set up a model where I do not reuse all of my motion mates, or my assembly mates. So I'm going to add some very motion-specific mates to this assembly and maintain the same motion but get to 0 redundancies. So the first mate that I'm going to do is I'm going to add a coincident mate between the axis of the piston and a point on the crankshaft. That takes care of one mate. The next thing that I'm going to do to keep the piston aligned in the piston sleeve is I'm going to select that vertex on the piston and this face on the sleeve. Now that will keep my piston aligned. All right, the second thing that I'm going to add is a hinge mate. For those of you not familiar with it, it's under the Advanced Mates option in our SolidWorks window. I'm going to add a hinge mate between the crankshaft and this bearing. All right. That's 3. Now I also need at this point to mate the connecting rod to the piston and the connecting rod to the crankshaft. So what I can do here is I'll just pull this out of the way a little bit so I have access to get to the faces that I need. And let's see here. We'll select that face there, add a concentric mate, and last but not least, one more concentric mate. And we'll exit that. So I've added 5 local mates to my assembly for motion. Now I'm going to turn on this parallel mate quickly so I get everything set back at the location that I want, and then I'll turn it off again. Now one thing to notice here, since I was doing all of those changes at the end of my timeline, these would not be suppressed until the 0.1 seconds. So what I'm going to do is roll that back and then delete each of these time steps. All right. Now the unfortunate thing is motion just reset my timeline. So let me go back and reset that to 1/10 of a second. Then we'll resuppress these at the beginning of our study. Another thing that I might want to do in motion, if I was interested, I could set up something called 3D contacts. What a 3D contact is, it allows me to tell motion that I'm looking for, say, this piston and the sleeve, and I want to have motion be aware of not only the materials that each of those components are, but possibly the friction between them. In this case, I can turn off friction if I want, so that would be perfectly perfectly frictionless. I can include that in this study if I want. In this particular model, it will not affect the results either way. All right, so again, I haven't changed anything with my setup as far as gravity or the forces acting on the piston or my rotary motor. Let me go ahead and suppress the solid body contact, and I'll just rerun this analysis. Okay, so let's take a look at some of the forces that are acting on this bearing. So what I'll do is go back into my forces and look at the reaction force Y component. In this case, the Y component would be a transverse loading acting on the bearing. And what I will do is select the hinge mate so that I can see the forces acting on that hinge. All right, let's take a look at one other thing. I can also take a look at the total magnitude of the reaction force acting on that hinge. How about I move this down here? And last but not least, I can also show you that I can query the X reaction forces. Those would be acting vertically in line with the piston for that same mate. Now if I line these up here, one thing you would be able to tell is that the addition of the Y forces plus the X forces is equal to the total magnitude of the forces acting on the hinge. Just like in SolidWorks, if I'm interested in seeing a little more detail, or I like to be a little more specific, I can rename a plot so that I know that's the Y force, acting on the bearing. Plot 2 would be the magnitude. And last but not least, this would be the X forces. I might also be interested in looking at the total power consumption of the motor. So if I do that, power consumption, I select the rotary motor, and I get a plot for power consumption as well. All right. So that's a simple model for setting up a piston and looking at the forces acting on it. All right, so let's go back to our PowerPoint slide here. So now that you've seen a basic setup, let's talk about our objectives for this model. We want to minimize the forces that are acting on the bearings, and once we've done that, what I'll do is step into optimizing our design. As far as optimizing the design, what we'll do is we'll change some of the dimensions of our counterweight. We can increase the offset, or the radius here. We can increase the arc of our counterweight. We can also increase the thickness of that counterweight. Now, let's not get ahead of ourselves. Let's go back and take a look at just setting up a design study. So what I'm going to do, right-click on my motion study. I'm going to create a new design study. By the way, this is available in SolidWorks Premium. What you can't do is optimization. So the first thing that I need to do is add some parameters. So what I'll do is, here we'll do a width. I'll choose a model dimension. In this case, we'll choose the width of this model. And you'll notice here when I'm setting up this parameter in motion, this asterisk under the linked column, this is what's telling me I am linking this parameter to a motion design study. Second thing we'll do is add an angle, which will be here. And the last but not least, we'll call this offset, and the offset will just be this radius. All right, now what that does is it makes these parameters available as variables in my design study. So the first parameter that I'm going to do is I'm going to add the width of this crankshaft here, actually that width right there. Let's say one of my design parameters I can go as narrow as 10 millimeters. Another thing that I'm going to do is change it rather than range with step. I'm going to allow motion simulation to vary that thickness anywhere between 10 millimeters and currently it's 15 millimeters wide. Second parameter I would be interested in would be the angle between these two faces of my crankshaft. Again, I'll choose a range. For instance, I might allow that to range between 75 degrees and 130 degrees. Now at this point I need to add a constraint. The constraint is actually going to come from a sensor that I'm going to add. So in 2012 I can choose motion data. I'm going to choose the study that parameter comes from. So in this case it's motion study 2. And I'm going to choose the Y directional forces, which would be this plot here. I'm going to look at the maximum force in the Y direction, and I'm going to turn off this alert. So there's my first parameter. And in this case, maybe what I'm interested in is having the transverse loading acting on that bearing as less than 15 newtons. All right. Another thing that I want to do is I'm going to minimize the mass of this assembly. So when I do a motion study and optimization, I need to have a goal. So in this case, the only goal that I'm interested in is minimizing the mass of the entire system. And that since I'm only changing parameters on this crankshaft, that's what's going to change. All right. Now when I run this design scenario, now I get some forces, the transverse forces acting on this bearing. And we can see here that the design study has come back and given us a minimum mass as we would expect. at the minimum values for these dimensions, 10 millimeters on the width and 75 degrees on the wedge. Let's go back in and add another variable. In this case, what I'll do is change the radius of this crank, and let's say I can vary it from 28 to 50 millimeters. Now again, I'm rerunning the study. I've reset the size of my crankshaft, and I'm going to rerun my design study. Now you notice here each of the times that I have the dark pink box, what that tells me is this particular iteration does not meet this this constraint. In our scenario here, we wanted to make sure that the transverse forces acting on our bearing were less than 15 newtons. So I can see I have several iterations that don't meet those requirements. Now what simulation motion has done is it has said that this is an optimum design. It's minimized the mass to be about 2.04 kilograms, and I have 9 newtons of force acting on my bearing. But you'll notice I have a couple of other instances here. For instance, I have iteration 4, where I have a mass of around 2.2 kilograms, but I have a lesser force by half a newton, transverse load acting on my bearing. So let's go back and take a look at our initial view here. Go back to our variable setup. Let's say I want to do one more step. I want to not only optimize on the mass of my design, but I also want to optimize on the transverse forces acting on this bearing. All right, so in this case, what I'll do is rerun the motion study once, go back to my design study, and I'm going to rerun the optimization of this piston. So I've added a few more scenarios. I went from 11 to 15 scenarios by adding the third variable. And you'll notice here that now I have an optimum design that's slightly over 10 millimeters on the width of the crankshaft wedge there, 75 degrees, which is just a shade above the minimum angle we're allowed. But if I reduce the radius of that edge there to just over 35 millimeters, you notice that the mass is around 2.1 kilograms, but I've even further reduced the transverse loading acting on that bearing. Now if I want, I go back to my optimum design, and then I'm going to go right back into the motion study, and I'm going to rerun this so I get a true representation of what's happening. And we'll notice that the actual forces are not 5, but they're really in the neighborhood of around 3. All right, so let's go back here and take a look. Our original system, the mass was around 2.54 kilograms, and the maximum transverse load acting on that bearing was just over 21 newtons. When I was looking at optimizing with mass only, I could cut down the mass of that assembly to 2.04 kilograms and reduce the true load, transverse load acting on the bearings to about 12.5 newtons. And when I used an optimization looking for both optimization of the mass as well as the transverse loading, I had a little bit more mass than the optimal mass, a little over 2.1 kilograms, but I drastically reduced the transverse load acting on my bearings. All right, so that's how you can use motion for taking a look at forces acting in your system and getting results on different entities that you might be interested in. All right, now as far as this goes, as engineers we would have to decide, would the optimized mass design at 2.04 kilograms be more efficient, or would we really want to minimize the forces acting on our bearings? Those are decisions that you would have to basically discuss and determine which is more appropriate, save money on the cost or make your products last longer. All right, so what I showed you today is motion analysis and design studies. Those are available in SolidWorks Premium. If you have Simulation Professional or Simulation Premium, you can do optimize your design with SolidWorks Motion. Also, I'll mention if you do have Simulation Professional or Simulation Premium, you have access to event-based motion. What that is, it allows you to choose things to happen in your assembly based on triggers rather than a pure timeline, as we worked on these examples. I showed you the integration of motion analysis in our SOLIDWORKS window. It's no different than just working on SOLIDWORKS models. We have a very familiar interface as far as inputs and outputs with our feature manager. And last but not least, I showed you motion studies, setting up mates for motion, eliminating redundancies, and I showed you how to go through the post-processing, set up plots, and look at results for what's happening on screen. And then we finished with a design study and optimization.